Hello, welcome to today's webinar. My name is George Janel. I'm a software engineer here at MBF Bioscience, and today I'm co-hosting this session with Mitchell Sendo, who is the product manager for ScanImage. So just a note, this webinar will be recorded, and the recording will be available later this week on YouTube under the MBF Bioscience channel. So the topic for today is ScanImage Simplified, a deep dive into the new Streamlined interface. So here's an overview of what we will cover today. We'll start with a brief overview of MBF's two-photon solutions. Then we'll dive into the latest ScanImage release, ScanImage 2026. We'll show you the new user interface. We'll talk about some exciting new features. Then we'll also give you some pointers for getting started with the new version. And at the very end of the webinar, we'll have time for a Q&A session. And on the bottom of your screen, you should see a button with the label Q&A. When you click on this button, it brings up a window where you can type in questions. So you can ask questions at any time during the webinar. We'll just collect these questions and then go through them at the very end. So let's start with a brief overview of a two-photon system. So a two-photon microscope is a very complex instrument, but I like to think of it in roughly four parts. So there's the optics, which is all your lenses and mirrors and half-wave plates and beam splitters and also all your actuators and motors, basically all the physical components that are on your optical table. A two-photon microscope is a computer-controlled instrument. So that means you need software to control your microscope. And the role of the software is to control all the components on your optical table and ultimately collect data and form an image. Then we also need a way for the software to actually communicate with all the components on the optical table. And for that, we use some specialized electronics, which is known as data acquisition electronics. And ultimately, all of these different parts are centered around a biological experiment, right? So all of these different parts need to work together to enable the biology that we actually want to investigate. So let's talk about these individual puzzle pieces in more detail. So first, let's take a look at the software. So MBF Bioscience develops a software called ScanImage. ScanImage is a software package for controlling two-photon laser scanning microscopes. It's MATLAB based. And one of the advantages of ScanImage is that it's completely source accessible, right? So you can open the MATLAB code, you can inspect it, you can customize it if needed. It's also completely scriptable. So every button on the user interface that you see has a corresponding API call. And that means you can completely automate all the workflows in your microscope. The very basic functionality of the software is to form an image. But ScanImage is much more than that. It actually integrates into your experiment itself and can run some advanced features such as online analysis or photo simulation workflows. ScanImage is also compatible with a wide variety of microscopes, so you can pick from a list of commercial vendors that we support, or you can build your own microscopes. Next, let's talk about the electronics. So at MBF Bioscience, we developed the VDAC. The VDAC is a PCI Express card that goes into your computer, and it's an all-in-one microscope controller, right? So basically, this electronics piece is all you need to run your microscope. It is based on a Xilinx Kintex UltraScale FPGA, and we use that FPGA to do some of the heavy data processing that is necessary to form images, but also to realize some of the very tight timings that are necessary to control a laser scanning microscope. The VDAC comes in two flavors. We have one version that allows you to collect data from up to 4 photon detectors at 125 megahertz sampling rate. And that basically covers about 90% of the use cases and the microscope configurations out in the field. There are some experiments that use more advanced techniques such as time-correlated single photon counting or time demultiplexing. And for those advanced techniques, you might need data rates or like sampling rates that are much higher. So we offer a version of the VDAC that can sample from up to 2 photon detectors at up to 2.7 gigahertz sampling rate. On the bottom of the slide, you can see the breakout box for the VDAC. So this is basically where you plug in all your PNC cables and all the signals to control your actuators of the microscope, such as shutters and galvo mirrors and resonant mirrors and power control devices. And on that, in the breakout box, you see we have 12 analog inputs, 12 analog outputs, and 32 digital inputs and outputs. So the design goal, when we came up with the specifications for the VDAC, we basically thought of the most complicated microscope we could possibly imagine and made sure that we can control that microscope. And up to this date, we haven't found a microscope that the VDAC can't handle. So when you put these two pieces together, right, ScanImage, the ScanImage software, and the VDAC electronics, that gives you access to a wide variety of features. So here's an excerpt of a feature list of ScanImage, right? So we can do resonance scanning, we can do multiple region of interest scanning, we can do photostimulation workflows, photon counting, holography, and so on. So there's a wide variety of features that are available to you. But the most important thing to remember is we want to help you enable your experiment, right? So if you have a specific experiment configuration in mind, then you can always reach out to us and we can help you make your vision become reality. There are two versions of ScanImage. There's ScanImage Basic, and ScanImage Basic gives you access to basic imaging, right? So you can do resonance scanning, for instance. You can control a stage. You can acquire C-stacks, things like that, right? So basic imaging. For more advanced experiments, we offer ScanImage Premium, and on top of all the features of ScanImage Basic, you get access to a larger feature set, such as online analysis, photostimulation workflows, time demultiplexing, 3-photon support, and so on. And if you have any questions which version is right for you, you can always reach out to us and we can help you decide which version you should get. So which microscope can you use with ScanImage? Well, you basically have 3 options, right? You can buy a turnkey microscope from one of our hardware partners, such as Phenosis, Perspective Instruments, Pacific Optica, Thorlabs, or SATA Instruments. If you're more ambitious, you can build your own microscope. So ScanImage has a large library of software drivers for all sorts of different devices, including galvo mirrors, motors, objective positioners, SLMs, and so on. And you can pick basically your devices, put them all together, and then configure in ScanImage which devices you want to use and control the microscope that way. Or you can take a middle-of-the-road approach and ask one of our integration partners, such as INSS or COSYS, to build a microscope to your specifications. So they'll plan out the microscope for you, they'll install the microscope, and then also use ScanImage and the VDAC to run the instrument. MBF Bioscience also offers 2 specialized microscopes. The first one is the SLAB2 microscope, which is geared towards voltage and neurotransmitter imaging. It's a microscope that has very fast frame rates up to 1,000 hertz. And really, it's geared towards understanding how a neuron computes information. So you can sample hundreds of synapses at a time and then understand how the inputs of a neuron correlate to the output of a neuron. We also offer the VCAM module. So the VCAM module is not a microscope itself. It's actually a module that bolts onto any existing two-photon microscope. And it's based on the light beads technology that was developed in the Ali Pasha Basiri lab at Rockefeller University. And it allows you to do very high rates of volumetric imaging of calcium signals in large population of neurons. Great. So let's switch gears now and let's take a peek at the latest ScanImage release. So ScanImage 2026 is a very exciting release for us. It features a complete rewrite of the user interface. And I'm going to hand off this presentation to Mitchell now, who can give us a guided tour through the new interface.
Thanks, Gabe. Let's learn about the new ScanImage. So ScanImage 2026 is mostly the same ScanImage that you knew from before, but now it has a refreshed user interface, right? So everything can be done from a single window. The display of your image data takes a large center stage in a new, very versatile viewport. All features have been re-implemented except for SLM photostimulation, which will be brought in for the next major release. This refresh has been in development for the last 2 years, and in that time, we've implemented input from both new and experienced users alike. And so I hope you all like it. Now, changing the look of the software so drastically warrants some explanation for why we decided to do this. Well, an impetus was that MATLAB shifted to base their front end on Chromium. Now, Chromium is great. We've got new design tools. We can include HTML animations, vector graphics, etc. But now old ScanImage does not run in new MATLAB. And so over the last several years, we have had many ideas on how to improve ScanImage workflows in front-end architecture. And now that here comes a great opportunity to revisit the user interface and realize these ideas. So with that, here are the design considerations we proceeded with for this new ScanImage. Firstly, we wanted to reduce clutter. With so many windows, it was inevitable that they would overlap each other at some point. We want to reduce the entropy of conducting an experiment. And if we're dragging our windows around or digging them out of the taskbar after minimizing them, then we're losing focus on our experiment. Now we consolidate the display of all features of ScanImage into the one window. The one window dynamically suits itself for however you are using ScanImage. Things that aren't relevant to what you're trying to do at that moment are hidden, but are accessed much more sensibly. Second, we want to facilitate feature combination. There were certain instances in old ScanImage where, since features were edited in separate windows, the features were difficult to plan out holistically. Taken as an example, a combination of PowerBox and mosaic scanning features. Here, we are effectively able to determine the distribution of laser power over a mosaic scan using PowerBoxes. With all the features defined within the same space, the interaction between them becomes more clear. Last but not least, we wanted to refine our own GUI architecture to more easily develop for ScanImage going forward. Reusing established, simple, and thoughtful, well-featured components of the new interface should reduce our technical debt going forward. Now we can develop features faster without adding clutter and this more cohesive software. Now, let's get into the anatomy of the new scan image. Prominently in the center, we have the viewport. It displays everything relative to axes measured in microns. It's a blank map for you to chart an expedition of your sample with your stage. All your imaging data is displayed here, as well as graphics to plan your scanning for imaging, stimulation, mosaic scanning, your laser power distribution over the sample, online analysis, etc. Everything goes here. On the left are acquisition controls. Here you can configure your scan settings, ranging from everyday parameters to super user options, the same as before, just now organized by searchable tabs. Then you can start your acquisition and monitor acquisition progress from here as well. On the right of the viewport are the Z controls. You can set imaging depth, set up a Z stack, set limits for your Z stage, and define your power across the depth of the sample from here. We have the widget bar on the right. This shows the status of your devices, allows low-level control of these devices, and now, owing to Chromium, it is scrollable if you have more widgets than can fit in the height of your screen. Lastly, minimized here is the auxiliary panel. So this is for all the advanced large panel features in ScanImage. Here it is with the waveform controls added. The auxiliary panel, as well as the tabs contained, are undockable. To undock it, you can click this undock button, and it then inhabits its own window. So if you have multiple monitors, this is a great way to make use of them. Undocking is a feature of many panels, including the viewport and panels and tabs within the acquisition controls. Now let's see the new ScanImage in action. First, we'll cover basic acquisition. First, to set beam power, we can edit that from here. Then to start previewing the sample, we can click Focus. We can then use the histogram GUI to set the contrast. The even and odd lines of the image are out of alignment, so we'll fix it by clicking the Auto Adjust Scan Phase button. We can increase signal to noise in our image by increasing frame averaging. ScanImage now does color mixing by default. We can toggle visibility of channel 2 and auto contrast, and now our image is green, the combination of blue and yellow channels. We can change the color of each channel like so. And if we set our gamma like this, and our contrast like this, then we can highlight the brightest parts of the sample. To more closely inspect image data, you can zoom in and pan to see the individual pixels of the image. And you can zoom out to see where you are relative to the navigable space. We'll pin an image to the background, and we'll drag the yellow marker at the top right corner of the field of view to navigate the sample with the XY stage. You can quickly fill the viewport with the field of view by clicking this Find Field of View button. The image is a little out of focus on our confocal microscope here, so we'll adjust the imaging depth with our Z stage, like so. We'll pin again here, And then we can revisit the position from before by moving the stage to where we right-click in the viewport. Here we'll change the color and transparency of the first channel so we can see how the live image overlaps with the pinned background. If you are zoomed in like this, it is convenient to move the stage by holding Control and dragging from anywhere in the viewport. We can change the depth of imaging with our Fast C by clicking and dragging the blue marker in the Z view. The two yellow lines in the Z view are the depths where the background images have been pinned. We can alter scanning from the viewport too. To scale the scanned RY, click and drag the corner. And then to move the RY, you can click and drag the RY outline. Next, let's demonstrate stack imaging. To set up a stack, open the Stack tab. This reveals the stack graphic in the Z view. I'm using the blue marker to check the preview of the stack depths with a piezo objective actuator. Here we will do a stack using a motorized Z stage to acquire at each slice. We can set the top and bottom bounds of the stack to the currently imaged depth, coerced by step size like so. You can set the center of the stack on a particular depth, like so. You can also set the top and bottom bounds of the stack symmetrically by making it a so-called centered stack. We'll abort this current preview of the sample and then make sure that we have enabled our stack. I'm going to set the frames per slice to 30 frames so that the displayed image has less noise. And then we can click grab or loop to start the stack. As it is acquired, the yellow marker in the Z view is following the focal depth. The yellow marker is the display slider. Whatever depth this slider is left at determines which depth's image you will be seeing in the viewport. You can also press page up or page down keys to quickly traverse stack depths. You can pin each slice of the stack to the background, like so. Now we'll do a fast stack using our piezo objective positioner. To do so, we'll click this Fast C tab with the stack actuation GUI, and then to reuse the slices for the slow stack, click the copy slow Z stack definition. For this faster volume rate, we'll want to have 1 frame per slice and instead acquire 30 volumes for averaging. Piezo objective positioners typically exhibit a lag relative to the driving waveform. So here we'll open up the waveform controls panel to view the Fast C waveform. We'll also undock it for a larger view. Right now, it would scan a nearly perfect sawtooth waveform, which provides little time for the piezo objective positioner to fly back to the top of the stack. So we'll fix that by adding some volume flyback time. And we'll test the waveform now to see how well the objective positioner follows this waveform. Here we see we have somewhere between 10 and 15 milliseconds of lag between our desired position over time and our measured position over time. So we'll go ahead and add 15 milliseconds for actuator lag from our stack actuation GUI. We'll retest. This is much better. So now from the one window, we can click grab or loop to start our fast stack. Now, since fast C stacking goes through each slice very quickly, we leave control of this display slider to you. You'll notice the images are slightly noisier here, and this is actually a feature and not a bug. The frame averaging is now implemented in time rather than in frames. So since the rate a depth is imaged is the volume rate rather than the frame rate for a slow stack, there is less smoothing here in the same averaging window. While this may increase noise, it rejects representation of events in the image that happened after the averaging window. You could always just increase that averaging window if you want that more crisp image. We can give the display of this stack a different color and some transparency to compare this fast stack's images with that of the slow stack. Now we'll demo the mosaic feature. To do a mosaic, start by opening the Mosaic tab. Then we'll edit the tile size and tile spacing to 600 microns. We'll also specify 600 pixels in width and in height, so our resolution of our pixels is 1 micron per pixel. You can click the Add Mosaic button and click and drag in the viewport to draw an array of tiles. We'll abort our preview here and click the Apply button next to tile sorting so that tiles are ordered in such a way to minimize time in transit. You can open a second viewport, and we'll use this second viewport to view the live image close up on the zoomed in viewport while we keep the other viewport open so that we can view the progress from a stationary and zoomed out viewport. Each viewport can display the same imaging data with distinct settings from the histograms. Clicking within a viewport tells these GUIs which viewports to bind to. We'll go ahead and start our mosaic. We're showing this at 10 times the speed. And now that we have our beautiful mosaic, we can get rid of the second viewport and zoom in on the pinned background of images. We can hide just the mosaic outlines from the Layers GUI for a cleaner view of the mosaic. Let's go over a few premium features. If you would like, we can talk more about them in office hours, which are every Tuesday from noon to 1 p.m. Eastern Time. They are also documented in the online documentation. But we'll get started with the VCam here. So the VCam, our product using the Visiri Labs Lightbeats technique, has some software accommodations made for it now within ScanImage. We can display captured data at the depths that they were collected, and we can account for lateral offsets of images through Z exhibited by the light beads. There are some other special accommodations for accuracy of display, accounting for resonance scanning with uniform sampling of lines and a single laser pulse per pixel sampling strategy, but I won't delve into that here. The characterization of the position of image data through Z is not just for light beats, but for all scanners. I think that this can be a step forward in accounting for minor misalignments of the system to make 3D optogenetics more feasible as we reliably place image data where it was acquired and then define stimulations relative to that. So ScanImage traditionally outputs image data in the TIFF format, and now ScanImage is going to output image data in an exciting new way. In ScanImage 2026, you can stream image data out via TCP/IP. We use the 0MQ library, which has bindings for every major programming language, such as Python, Java, JavaScript, etc. You can write your own program for online data analysis or closed loop behavior or whatever else you can think of. The data transfer is lossless and has low latency, and we're excited to see what applications you are going to implement with this. Now let's look at how you can get started with new ScanImage. There are 3 things you can do to make the transition smoother. You can just talk to us, contact our support, and we can walk you through software personally. We have new documentation on the new workflows, complete with videos. I suggest watching those for quick starts and reading for detailed understanding. And 3, we have a little transition tool. Aside from general workflows, there may be moments where you're just looking for a particular control from before and having trouble finding it. Well, this helps with that. You can access the transition helper from the help menu, and this will bring up all the old windows of ScanImage, though a little worse for wear. When you click a control in the old interface, It navigates to and blinks the corresponding control in the new interface. Give it a try, but do so well in advance of an actual experiment. It should be noted that there is a small hike in system requirements. If your CPU was released before 2013, then you'll need a new CPU. This version of ScanImage runs on MATLAB 2025B and was tested in MATLAB 2025B. Also, we recommend a 2K monitor, though a 1080p monitor will still fit everything. And now I'd like to open the floor to any questions that we have. I see some questions about this 0MQ implementation. We have a specific question about whether it supports zero copy sharing via the Windows API. Can't
So
specifically.
yeah,
Take
I can answer that. So we do not use a zero copy mechanism. So right now um, we use we basically use a TCP/IP socket with the publish subscribe pattern.
And the 0MQ pipeline is achieved through our acquisition MEX file.
Right. So you cannot directly access the 0MQ stream from within the ScanImage MATLAB interface. The entire point of the 0MQ implementation is that it directly pipes the data out from the source um, to basically the consumer, right, over TCP/IP. And we did not want to have MATLAB in the loop there because that introduces additional latency. And if MATLAB is not keeping up with your image acquisition rate, then you might drop data. So the design goal of the 0MQ interface was to have a lossless data transmission and very low latency. So there's no MATLAB involved as a middleman.
I see one question is, how does one view multiple images from temporally binned virtual channels? So yeah, there's the color mixing, but if you don't want your channels to be mixed in color, you can add multiple viewports. If you want to see, for example, if this is light beats, then separating them by depth, you can do that from the viewport as it was shown with the display slider, but also there is a analog to the tiled display mode from old ScanImage, so you can display all of your depths simultaneously on the screen.
One question related to the compatibility of scripts that users might write to automate their workflows. The question is, are those scripts still compatible with the new ScanImage version? In doubt, you can always reach out to us and we can help you, modify your scripts to be compatible. But the general guideline is that the backend of ScanImage itself has not changed or not changed much. So if you access components in ScanImage like the photostim module or the scan2d objects, all of that is the same. What has changed is the interactions with the user interface, right? So if you try to access um, the user interface directly over HSI controller, for instance, that has changed and that would need to update. I'll take another question here. Does the 0MQ interface accept commands like start, stop, focus? The answer is right now, the 0MQ interface that Mitchell presented is purely an output, right? So it's basically ScanImage in this case acts as a server that just starts streaming data, and then you as the user can connect to the data stream. By default, ScanImage does not accept, commands over TCP/IP to start, stop, or otherwise control the acquisition. That being said, is we have some other projects where we have implemented functionality like that. And if you're interested in that, please reach out to support and we can get you up and started with that.
I see a question where, oh, where they're talking about line scan feature in ScanImage, and whether it's been implemented that we are acquiring that data to TIFF rather than the kind of specialized pmt.dat file format. And the answer is no, that is the backend is mostly the same, but there was previously in support somebody asking the same question, and we have developed some scripts to post-process that data into TIFF or even into Chimograph. So that may be useful to you.
Um, so one question relates to scanning artifacts in ScanImage when the line phase is not correctly adjusted. So the user is asking, when you start an acquisition, the line phase is off. Then you adjust the line phase and the image looks good, but then you change zoom and the line phase is off again. The reason for that is that the line phase setting might be different for different zoom levels of the resonance scanner. ScanImage internally builds up a map whenever you change the zoom level. It remembers for a specific zoom level what the setting is, and then tries to interpolate. So it's basically builds up a lookup table. If you find that that does not work correctly, you can open up that lookup table. There's a small graphical user interface that allows you to modify that lookup table. And adjust it to your scanner again. So that's an option. And if you want a demo or want to know how that works, feel free to reach out and we can help with that.
I see a question. Are there changes in hardware support? Is it possible to potentially use other FPGAs, etc.? How separate are waveform control in resonant mode and a digitization part? I don't know if I'll cover all this question, but there essentially are not changes to our hardware support. We still support medium and high speed VDAC and the supported National Instruments hardware architecture that we supported since the beginning. Not the current ones that we support from our documentation. The waveform control in resonant mode, there is kind of some following of the resonant frequency. If it drifts, then we are following that with our waveform control. So there is some feedback there. And yeah, I think I'll leave it at that. But we could talk more if you want.
There's a question about the VDAC and its use with silicon photomultiplier detectors. And specifically if the VDAC has an increased input range. And the answer is no. The VDAC input range, the maximum input the maximum input range of the VDAC is -1 volt to +1 volt. That's a limitation in hardware and the design choice of the VDAC. If you want to maximize your dynamic range of the VDAC, it is advised to find a way to set a bias on your photodetector so that basically no photon level sits at -1 volt, and then basically use a 2 volt dynamic range of your photon detector.
I guess I like this question about tiling. Says, I am wondering why mosaic tiles need to have their size and resolution specified. Is it not possible to match the field of view from focus and simply move it by specified displacement in X and Y? That I like that idea. Just not the way we did it, but it could be easy enough. Make a drop down for different modes of specifying those types.
That being said, right, the tiling or the mosaic functionality is completely scriptable as well. So if you have a specific algorithm in mind, you can always, specify tiles yourself and arrange them in any way. So that's definitely a possibility. So you can automatically generate that mosaic scan and have any type of order of the tiles and any type of configuration of the tiles you want to.
This question, if the microscope setup allows adjusting the laser power using a half-wave plate, what would be an efficient way to dynamically adjust the laser power during a tiled mosaic Z-stack acquisition? For example, changing the laser power as a function of depth. I mean, it's kind of hypothetical, but I guess you could like sort if you, I don't know, you have to, I'm thinking you would sort tiles by power and then sort tiles by distance from each other and um, try and make the best of whether you think it'll take more time to transit from this tile to this other tile over here with the same power, or take more time to rotate that half-wave plate. Um, but hopefully I'm interpreting this question right. But um, yeah, hypothetical, not incorporated into ScanImage.
Um, there's a question, can two different masks or ROIs in a single field of view be illuminated with two different laser powers? And the answer is yes. For each ROI that you specify, by default, it uses, the global laser power, but you have a way to specify and override the laser power for each ROI individually. And also you can specify multiple masks for power boxing if needed. There's a question, is it possible to pin previously acquired images to the background before starting a new mosaic scan? For example, to perform an alignment to re-image the same spot? And the answer is yes. You can do that, of course, right? So anything that you pin to the background stays there until you clear it. You can also, if you have a background pinned, you can save that background out into files and then in the next session, the next day, for instance, load that background back in and also align the background to the current imaging session. There's a special alignment tool that Mitchell implemented for that.
Yeah, I was going to bring that up. Uh, yeah, once you've done that alignment, then the idea is that all of the sample positions that you might have saved for mosaic or maybe cycle style scanning, you can reuse those sample positions. Um, so yeah, save those mosaics or uh, cycles to file and then save and then load between sessions on the microscope. You can account for a 2-degree shift of your sample, you know, um, more easily now than before. Well, I would like to reiterate my thanks for all you taking time to join us today. Please don't forget to fill out the short survey at the conclusion of the webinar. Your feedback is an important component to our continuous improvement process. For general questions, discussions, frequently asked questions on anything from general imaging and analysis to worm tracking or multiphoton imaging, we would like to remind you we have forums where users can communicate with each other and MBF experts. This is at forums.mbfbioscience.com. We welcome all your input and look forward to hearing from you. And also, we invite you to our weekly MBF Bioscience open office hours. This is a great opportunity to connect directly with our scientific and technical experts, ask questions, and get tailored advice specific to your research.
Well, thanks everyone again for joining, and hopefully you're going to have a great time with the new ScanImage release.